Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In this lecture, we deal with the topic Kmap or Kmap. During the last session, we have learned to simplify Boolean expressions using postulates and theorems. There, the expression was simplified in each step by applying postulates and theorems, and we finally ended with a minimized logical expression. This is a time consuming process. In this class, a new method of minimization is introduced known as Kmap or Kmap. A Kmap is an array of cells that represents a binary value of the input variables. It provides a systematic method for simplifying Boolean expressions. It produces the simplest sum of product or product of sums expression possible, known as the minimum expression. Kmap can be used for the expressions with 2, 3, 4 and 5 variables. The number of squares or cells in a Kmap is 2 raised to n, where n is the number of input variables. Let us prepare a 2 variable Kmap for a product of sums expression. Here, the number of input variables n is equal to 2. Hence, total number of cells in the Kmap is 2 square, that is 4. See the table here. The input variables we refer are A and B. Each row is headed by the possible values of A and each column is headed by the possible values of B. When you represent a product of sums expression, each cell represents a max term. Just recall, 0 in max term is symbolized with an uncomplemented variable and 1 using a complemented variable. One more important point to be noted is that only a single bit position difference is allowed in adjacent cells. For a 2 variable map, it does not matter. By looking into the row and column heading, we are able to fill the cells with corresponding max terms. When the row heading is 0 and column heading is 0, the max term we write is A plus B. When row heading is 0 and column heading is 1, the term is A plus B complement. Likewise, we can write all max terms in the corresponding cells. Let us also create the 2 variable Kmap using min terms. See the table, when you represent a pos expression, each cell represents a max term. To represent a SOP expression or sum of product expression, fill the cells with corresponding min terms. So, when the row heading is 0 and column heading is 0, the min term we write is A complement dot B complement. When row heading is 0 and column heading is 1, the term is A complement dot B. Likewise, we can write all min terms in the corresponding cells. Next, how do we draw a 3 variable Kmap? 3 variable means we will have 2 raised to 3, which is equal to 8 cells to represent the function, and it can be written as shown here. Here, values of input variable A is given across the rows and values of B, C across columns. This can be changed with the convenience of the user. It is possible to write AB on row wise and C on column wise. Notice the binary sequence across columns. After 0, 1, we write 1, 1 because, as I mentioned in the beginning, only a single bit position difference is allowed in adjacent cells. So, what is exactly meant by adjacent cells? Cells having single bit differences. Consider the values 0, 1 and 1, 0. The cells representing these 2 values are not adjacent because both the bits are changed or bit difference is 2, which is not allowed. So, we must be careful while writing the binary sequence for n greater than 2. In the same manner, you can also draw the 3 variable Kmap for a product of sums expression. Before moving to simplification of the Boolean expression, let us also see how to write a 4 variable Kmap. we have 4 variables, say A, B, C and D. So, total number of cells required equal to 2 raised to 4 equal to 16. And the min terms can be arranged in such a way that first 2 variables A and B are written across the rows and next 2 variables C and D are written across the columns. So, Kmap is a 2-dimensional array of cells in which each cell represents the value of its input variables. Now, let us see how cell adjacency is maintained in a Kmap. The cells physically next to a cell in all 4 sides are adjacent cells. See the picture here, but diagonally it is not. Also, cells in the top row and the corresponding cells in the bottom row keeps 1 bit difference. So, they are adjacent. Check the elements of leftmost and rightmost columns. Yes, the corresponding cells are adjacent to each other. The figure clearly shows the cell adjacency in a 4-variable Kmap. As stated above, a Kmap is used to minimize the Boolean expression. To simplify a sum of product or product of sums expression, what we have to do first is to represent the expression in the Kmap. While mapping a sum of products expression, we have to write a 1 for each product term that appears in the expression. For example, if we have a term A, B complement, C complement D in the expression, we have to write 1 in the cell 1, 0, 0, 1. After mapping all terms to Kmap, you find a set of 1s in several cells. The remaining cells can be marked as 0 or you can just leave it blank. Before you start mapping, make sure that the expression is in standard form. Otherwise, convert to standard form and proceed to mapping. Consider the function A complement B complement C plus A complement BC plus A B complement C complement plus A B complement C. How do we represent it in Kmap? Draw Kmap for 3 input variable. Then insert 1 in the corresponding position of each product term of the function and we get a map like this. If the expression is in non-standard form, we have to convert to standard form. To illustrate, consider the function AB complement C plus AB plus C. It is a 3-variable function, but 1 variable is missing in the first term and 2 variables in the second term. We have already discussed the conversion to standard form in one of the previous sessions. As we discussed there, introduce the missing variables AB complement C plus AB into C plus C complement plus C dot A plus A complement dot B plus B complement, which is equal to AB complement C plus ABC plus ABC complement plus ABC plus AB complement C plus A complement BC plus A complement B complement C. Remove the redundant terms. Then we get AB complement C plus ABC plus ABC complement plus A complement BC plus A complement B complement C. This is the standard sum of product expression equivalent to the given expression AB complement C plus AB plus C. Then map this standard expression to Kmap for minimization. So, now we learned to express a standard or non-standard sum of products function in a Kmap. The Kmap is ready for minimization now. What's next? Reduction of terms and variables. How? First, we have to group ones. When we group ones, we aim at maximizing the size of the groups and minimizing the number of groups. The groups are formed using only ones and we consider only rectangular form of groups. Diagonal formation is not allowed. In each group, the number of cells, that is number of ones, should be power of 2, means 1, 2, 4, 8, etc. or in general it should be 2 raised to n. Include the maximum possible number of ones in a group as it is shown. Each one should be included in at least one group. If any one left ungrouped, as it does not have any other ones in adjacent cells, that itself can form a group. Groups can be overlapped. The groups may also wrap around the map. The ones in the corresponding position from top row and bottom row can be grouped. In the same way, ones from leftmost and rightmost columns can be grouped as shown in the figure. Here, a 1 from the top row column 1 is grouped with a 1 of bottom row column 1. This is called map rolling. A pair, quad or an octet can be formed by combining the adjacent ones in rectangular form. When two ones are combined, it is called a pair. When there are 4 ones, that is a quad. And if the group consists of 8 ones, we call it octet. A combination can also be obtained by map rolling, that is rolling the map along its length or width. Here in the map, you can find a 1 which has no adjacent ones. Such isolated elements must also be considered as a group. It may so happen that a group which has all its values also contained in some other groups. We call it a redundant group. A redundant group must be removed, otherwise it will add an extra term to the expression. Formation of groups in a 3-variable Kmap is shown here. You can form a pair of ones or quad either by just combining the ones or by map rolling. You may also find an isolated one as a group. Formation of groups in a 4-variable Kmap is shown here. You can form pair of ones, quad and octet either by just combining the ones or by map rolling. The overlapping techniques are also shown here. The next, we are going to learn how to determine the simplified Boolean expression from the Kmap. From each group of ones, we get a product term in the expression. This product term is composed of the variables either only in true form or only in complement form in all terms of the group. For example, look at the Kmap given here. Two groups of ones are formed. In the first group, the terms involved are A complement B, C complement D and A complement B, C, D. When you notice these terms, the variable C takes true form in one term A complement B, C, D and complement form in the other A complement B, C complement D. Such a variable is called contradictory variable and it is to be eliminated from the resulting term. The variables that appears only in any one of the form is retained. So, the term generated from this group is A complement B, D. C is eliminated. In the same way, consider the second group which has 4 variables A, B, C and D, where B takes both the forms, that means B is a contradictory variable and we remove B. Thus, the second group produces the term A, C complement, D complement. So, the minimized expression of this Kmap is A complement B, D plus A, C complement, D complement. In general, we can say a pair of ones eliminate a single variable and its complement. What if we group 4 ones? Group of 4 ones can be called as a quad and it eliminates 2 variables and its complements. For example, in the Kmap given here containing 4 terms A, B, C, D, A, B, C, D complement, A, B complement C, D and A, B complement C, D complement. Which are the variables remains in a single form? Let's take one variable each. A has the same true form in all 4 terms. So, we can consider A in the resulting term. So, let's write the resulting term A. Next, we take B, which shows a true form in the first 2 terms and complement form in the next 2. So, the variable b is to be removed. Next, take the variable c which appears same in all 4 terms. So, we add it to the resulting term. Now, the result term is ac. Lastly, let us consider d. It takes both forms and so it is a contradictory variable. So, we do not include it in the resulting term. At last, see what is the expression produced out of this group? It is ac. Only 2 variables or 2 variables are eliminated, and hence we reach to a conclusion that a quad eliminates 2 variables and their complements. When you combine 8 ones to a group, it forms an octet, and an octet eliminates 3 variables and their complements. And the special case, what happens when all cells yield to 1 that forms a single group in a Kmap? In such a case, the value of the expression will be 1. Now, let us use a 3 variable Kmap to minimize the expression a complement b complement c complement plus a complement b complement c plus a complement bc plus abc plus ab complement c. Let us first draw a 3 variable Kmap. We write AB across the rows and C across the columns. Now, inspect each term. A complement B complement C complement refers to 0 0 0. So, enter 1 to this particular cell. Next, A complement B complement C which refers to 0 0 1. Write 1 to the corresponding cell. Then A complement BC, that is 0 1 1. Enter 1 to that cell. Then we have ABC corresponds to 1 1 1, give an entry 1 to this cell. And the last term AB complement C, that corresponds to 1 0 1, and enter 1 in the respective cell. Yes, the complete expression is mapped to the Kmap. What is next? We have to group the ones. Try to make minimum number of groups with maximum number of ones. We get 2 groups. All ones are grouped now. Now, we start reduction. The first group is a pair from where the variable c is eliminated because c takes both 0 and 1 value. So, the term is AB. Next group is a quad. The variables a and b are to be eliminated because both variables changes the forms along the terms from 0 to 1 and from 1 to 0. So, a and b are deleted. So, the reduced term is c. Thus, the minimized expression is AB plus c. This can be implemented using an AND gate and an OR gate. The circuit is simplified to minimum number of inputs as well as reduced number of gates. Let us draw the logic circuit. Remember, this can be applied only if the expression is in standard form. If a non-standard function is given, convert it to a standard function by using the method we discussed in the previous sessions and then proceed to Kmap. It is also possible to map directly from a truth table. Let us see how to do it. Consider the truth table that is shown here. It is constructed with 3 input variables A, B and C, and the output is denoted by X. Recall that a truth table contains output for all different input variable combinations. In this truth table, the output X is 1 for 4 input combinations 0 1 0, 1 0 0, 1 0 1 and 1 1 0. These terms can easily be mapped to a Kmap. So, we draw a Kmap with 3 variables and mark 1 in the corresponding cells that yield to 1 in the truth table. Other cells yield to a 0 value. You can either write it in the map or just leave those cells blank. Then, as we did earlier, we start grouping. Here we get 2 pairs. We know that a pair eliminates a single variable, and in the first group the variable A takes primed and unprimed forms and it is eliminated, and the reduced term is B, C complement. and for the next pair C is removed and the term becomes AB complement, and hence the minimized expression is F equal to BC complement plus AB complement. Sometimes you may find the question in this way: F of ABCD is equal to summation of 0, 2, 4, 6, 7, 8, 9, 14, 15. It is nothing but the compact form of a canonical sum of products expression. Focus on the terms, each corresponds to a min term that outputs a 1 for the Boolean function. Let us convert it into a sum of products form. The first term is 0, that is M0. The binary equivalent is 0, 0, 0, 0, which is represented as A complement, B complement, C complement, D complement. Recall that A, B, C, D is ordered. You can just refer to the module on canonical forms for better understanding. The next term is 2, that is 0, 0, 1, 0, and the corresponding term is A complement, B complement, C, D complement. In the same way, we will write all other terms 0, 1, 0, 0, that is A complement, B, C complement, D complement. Then 6, that is 0, 1, 1, 0, A complement, B, C, D complement. Then 7, 0, 1, 1, 1, A complement, B, C, D. Then 8, 1, 0, 0, 0, that is A, B complement, C complement, D complement, and 9 is 1, 0, 0, 1, A, B complement, C complement, D. Then 14, 1, 1, 1, 0, it is A, B, C, D complement, and 15, 1, 1, 1, 1, it is A, B, C, D. So, F of A, B, C, D is equal to A complement, B complement, C complement, D complement plus A complement, B complement, C, D complement plus A complement, B, C complement, D complement plus A complement, B, C, D complement plus A complement, B, C, D plus A, B complement, C complement, D complement plus A, B complement, C complement, D plus A, B, C, D complement plus A, B, C, D. This is the Boolean expression. Next, map this expression to Kmap. Enter 1 to each term that exists in the given function. The next step is grouping ones. We can form 2 quads from here. Then 1 pair. 3 groups are formed: group 1, group 2 and group 3. The reduced term of group 1 is A complement, D complement. The reduced term of group 2 is BC, and the reduced term of group 3, that is a pair, which is A, B complement, C complement. And finally, the simplified expression is the sum of all these terms, that is A complement, D complement plus BC plus A, B complement, C complement. We can verify the answer from the truth table. The truth table for the expression F of A, B, C, D equal to summation 0, 2, 4, 6, 7, 8, 9, 14, 15 is shown here. The simplified expression is A complement, D complement plus BC plus A, B complement, C complement. What will be the value of this function when A equal to 0, B equal to 1, C equal to 1 and D equal to 0? Assign these values to the simplified expression. Then it becomes 0 complement dot 0 complement plus 1 dot 1 plus 0 dot 1 complement dot 1 complement, which is equal to 1 dot 1 plus 1 dot 1 plus 0 dot 0 dot 0, which is equal to 1 plus 1 plus 0, which is equal to 1. The same is given in the truth table. You can check with any possible input combination and confirm the minimized expression. The basic details to represent a Boolean function using Kmap is described here. We have reached the end of this session. We may now summarize the topics discussed. A logic circuit can be represented in different ways using Boolean expression, truth table and Kmap. When the Boolean expression is complex, the circuit also becomes complicated. So, there is a need of simplifying the expression by which we will be able to have a more simpler logic circuit. Here, we have used the tool Kmap to simplify the expression. Each term in a Boolean expression can be represented in a Kmap, and by recognizing the various patterns or groups formed, we are able to derive a minimized logical expression. Minimization of sum of products expression was detailed in this lecture. Minimization of product of sums expression and a special case don't care condition will be explained in detail in the forthcoming class. Thank you for watching. See you in the next session. Bye.